So my name's Bill Brown, for those who don't know me. I'm field sales agronomist with Growmark. And we've been working on the custom training sessions for quite a few years. Barry Hanna, most of you remember Barry. He has a new position now as head of human resources. And but he kind of got the things going, and he's worked with helmets for quite a few years, and we just carried on and been doing that for quite a few years. So presentation.
Jason was just chomping at the bit after hearing Jim's presentation.
Well,
I want to go next. I want to go next. So obviously we've gotten, he's got a burr under his saddle for something, and he's hopefully going to share. Jason was going to talk about temperature inversions, but you're still on that.
No, I don't know. I think I'm going to let it go. You guys your eyes are rolled back enough to hear any more about droplets. Maybe one.
No, never let it go.
I can't resist.
Don't give up the chance to win.
How long did it take for people to start to glom onto the color system for nozzle rates? Fine, very fine, medium, coarse, very coarse. Helmet's been hitting you over the head with that for a long, long time. And a lot of you guys are working that way. You're doing the best you can. I want a larger droplet because it won't drift. I want a smaller droplet because it's got good coverage, and we just sit on that teeter-totter. But there's a really important piece of information that's missing, and I'm going to muddy the water even more than it has been already. So be prepared for you to just ignore everything from this point on. Here is a simple graph. Here's the size of the droplets. We've got 100 microns, we've got 200, 300, 400, 500.
Jason, maybe to put it in perspective, 100 micron
So we've got
is about the size of a human hair.
Yeah, we're into the fine range here, we're into the very coarse range here. And depending on who you ask, GABE or even TJET, they'll cut that pie up and they'll just sort of arbitrarily say, okay, everything from here on forth shall be known as coarse. But for our sake, we'll just keep it a sliding scale. You get a nozzle because the nice people at TJET say it's a medium, which probably fall around here-ish. How do they know that the droplets that come out of that nozzle are medium? How do they know?
Measured it.
They measured it, sure. They fired it through a laser at a certain temperature with a certain viscosity, and they've defined, this is the nozzle we're going to use as our standard, just like the product you chose, and these are the parameters we're going to use, and then we fire this thing through a laser, and we get the average. The average size droplet that comes out of this nozzle is medium. Therefore, we're going to call this droplet, this nozzle, medium. Here is a medium. Here's a medium. They're both medium. The average number of droplets that came out of there were about 300 microns. What's different about those two nozzles?
You know, a wide range on the.
Holy cow! Are there ever, look at that. So you go out and buy a medium nozzle, and your buddy goes out and buys a medium nozzle, and one guy drifts into the next county. And you go, I don't get it. We did everything the same. We both had medium droplet nozzles. You're missing the range, the variability, the standard error. The average income in this room, sadly not enough as it should be. It doesn't mean anything, because we don't know who's making a fortune and who's barely scraping by. Without that scale, that number doesn't mean anything to us. So they're starting to push nozzle manufacturers to sort of fess up. Fess up. I've even seen data where nozzle fractions look like this. Whoop. Been a long time since I've used chalk. Bimodal. Average is the same, but we got a whole bunch of fines, and then we have a whole bunch of mediums. Until you know the spread, you don't know anything. So when you see a volume fraction, Jim was, that was the first time I've ever seen efficacy data overlaid with drift, by the way. It was really nice to see, because you finally really get a good view of that balance. What means more, the potential for drift or the potential to get the job done? And, well, it depends. Who's nearby? What are we spraying? Who's watching? Here's his data. I'm starting to muddy this up. Here's a volume fraction. Let's say the cutoff was 210. We heard that this morning. Maybe one of those nozzles, 5% of everything that came out of it was smaller than 210. So about that part. And then another nozzle only 4% of what came out of that nozzle was under 210. And you go, well, 4% driftable fines versus 5% driftable fines, it's a no-brainer. I'm going to go with the 4% because there are less driftable fines. Ah. But that fraction that was smaller than 210, did it go all the way down to like 25 microns? Or did it stop at like 185? Is it better? Okay, I'm spraying 4% of my spray that comes out of my sprayer is smaller than 210. But that 4% goes all the way down to a little 25 micron dust mote that can go for kilometers. Versus maybe it ends at 180. It'll still drift, but exponentially not as far as the really small stuff. So we were just talking about this without those error bars, just going on the average alone. Yeah.
Do you see that this will, that the size classification will change?
I see this as
In
one
print?
more confounding factor. So, you know what I'd rather see instead of, if I'm thinking of drift, I don't want to know the medium or the mean. I want to know the smallest. What's the smallest droplet this nozzle is going to put out? 180. Okay, now tell me the average. Somewhere around 310. Those two numbers I need.
Okay.
And if you want to get really crazy, you know, you can talk about coarse too. One big drooly droplet is a huge fraction of what comes out of the nozzle, but it's not going to do you a whole lot of good. But as a general rule, that's not a big problem. There are nozzles out there called controlled droplet applicators, CDAs. Have you seen these? They're little spinning discs that have teeth in them, and the liquid hits the spinning disc, and it rides down a little ridge and gets flicked off. They look like this. They have very low variability. Their droplets are very uniform in size, and you can get different discs that put off different averages. But they stink. They're no good on field sprayers. They're almost like a rotary atomizer, and that's for planes. So all I'm saying is, and I just gave a talk in Leamington on statistics and little tricks you can play with them. If you get a mean in any talk, except for mine, you can trust me. If you get a mean in every talk and you don't get the variability, the span of the data, ask for it. Because there's something you're not being told. There, I'm off my high horse. And now for something completely different. So yeah, I was in Boise a couple of years ago and I heard Andrew Thostenstein speak. Great guy. And he talked about temperature inversions and blew me on my heels. What is the one environmental factor that we tell you guys to look out for when it comes to drift?
Inversion.
No!
Wind.
That's today. Yesterday it was wind.
Wind.
Oh my God, it's windy. Don't spray in the wind. The wind, oh, it's horrid. Go home. Wait for the wind to stop. But not completely stop. You need a little wind. And that's where we sort of been. Watch out for the wind because wind is drift. Some of the really attuned people will also talk about heat. It gets really hot, you'll get a lot of evaporation. But for the most part, our scapegoat has been wind. And then Andrew stands up and goes, yeah, wind's nice, but it's not the problem. It's inversions. And he proceeded to tell us why. Then a year later, while I was still more or less digesting what I had heard, he does a teleconference. People came in from all over North America. He did a longer version. It was awesome. It was so good that I stole it. Actually, I asked permission. So that's the man himself. And he gave me permission to take his talk and sort of condense it and illustrate it a little differently so that it was a bit more bite-sized for us. But I give him full credit for bringing this to the forefront and giving us a way to explain it more clearly. So, come on. What is pesticide drift? What is it if you had to define it?
Chemical going where it's not supposed to be.
Bingo. It's product going where it wasn't intended to go. Now, I told you I work with air blast sprayers. They come and introduce me that way, which means I get to see all kinds of wacky contraptions. Would you say that's an effective application? Possibly.
Yeah, depending on what you're trying to do.
Is it efficient? Not so much. But it makes for a great photo, and I love it.
There's the one that helmet was wanting behind the boom sprayers.
Yeah.
You saw the other hand with the video camera.
Isn't that crazy? And you should understand that anything under about 50 microns, you can't see. It doesn't refract light very well. That's just what you can see. What's nice is he only has to do 1 pass per acre if the wind's going right. There are 2 kinds of drift as we define them, and I've heard them explained a lot of different ways, but this is the way I like to do it. There's particle drift, and those are the drops. Or, if they evaporate enough, even the dust that they leave behind. And when we're talking particle drift, we're talking wind, possibly thermals. It goes on a scale of tens of meters. Although I have seen it go 500 meters. That's about the scale we're talking. And then there's vapor drift. This can happen long after you're done applying 2,4-D and dicamba, but scary right now. Known volatiles. They land, you go home, you're in the middle of dinner, and now it's starting to raise up off the plants, and it goes where it wants to at that point. That's more of a chemical issue. It can go kilometers. What can pesticide drift do? This is from Mike Cobra. I love this picture, so I played with it a little bit, try and clear it up. The herbicide was applied in that little bottom red area there onto soy and drifted over onto a tomato planting. What's neat, and I don't have this here, it's a whole different talk. See this jagged little line where it's all good here? They came back the next day to keep planting. So you can time when the drift occurred. That's very likely vapor drift because it went just so far, and they looked back and it wasn't a high wind. What they found out later is that was a temperature inversion that did that. Of course, we know pesticide drift is bad. It can do a whole lot of nasty things to the environment and or bystanders, and it's no good for neighborly relations. So let's get to it. What is a temperature inversion? Any guesses? Any closet meteorologists here? Not a clue. Honestly, is it that bad?
Different levels of heat at different ground.
Okay, good. We got a sense of it. We'll get a little Discovery Channel on you. Picture the Earth's surface. During the day, as the sun comes up, shortwave radiation starts to beat on the Earth and everything on the Earth, heating it up, which is why we get so red when we go to the Caribbean. The result is everything on the surface gets hotter. And if you look, as a sliding scale from the ground itself, up and up and up into the atmosphere and outer space, it gets from warm to cold. And that is the state of things. That's how we live a lot of our days. Until the sun sort of passes over noon and starts to go down, and everything that had all that heat really only borrowed it, because it starts to radiate all that heat back off the surface. Everything that had heat is going to lose it in the form of long-wave radiation. Depending on how quickly that surface spits off that heat, something really wild can happen. All of a sudden, the ground and everything on the ground gets really cold because it throws that heat off really quick. If it does it too quickly, it hasn't got a chance for that heat to dissipate. And what happens is, it's cold on the surface, then relative to that, warmer, because it hasn't gone anywhere yet, and then cold again. And you get this boundary layer of cold on cold. That is a thermal or radiation inversion.
Why doesn't it just keep going? Higher rises.
If it happens so quickly, it hasn't got a chance to go high enough, quick enough. And you get that warm layer of air just sort of stuck there. There was a great video that I tried desperately to rip off of YouTube to show this. It was a guy in Detroit, I think. He was a sort of a scientist magician. He liked to teach things with illustration. And he had two 2-liter pop bottles. One ice cold water, one hot water. And he dyed the cold one blue and the hot one red, because he was clever. And what he did was he took a playing card, put it on top of the nice warm bottle, and he put the playing card on the cold bottle, flipped it over, so that the two mouths sort of met. Hot on the bottom, cold on the top. What happened?
What was that again?
He had cold water on the top, hot water on the bottom, red and blue, food colors. What happened as soon as he sort of made them meet?
Hot should go up.
Yeah.
Convection. Hot rose, cold dropped, and suddenly we had a really neat purple color. Then he did it the other way around. He put hot on the top and cold on the bottom. When he pulled the playing card out to let them mix, what happened? Nothing. Nothing. It was stuck. The cold couldn't get above the hot. It formed a layer Why do we care? How does that cause drift? They did this really neat thing. This is from a buddy of mine in Washington. They sprayed rhodamine dye during some aerial application calibration tests. That's just red dye coming out of a plane. They did it during an inversion. And it's a little clearer up here on the screen. There is a layer of pink at about neck high. And it's just sitting there. I mean, it's going nowhere. None of the dye hit the ground, or very little anyway. Most of it was trapped right there in that layer because it's still, it's not mixing. The cold can't get any higher and the warm is stuck too. It just didn't spit off fast enough. And there it sits. So when pesticide, either a particle, a very fine, or even a vapor, gets trapped in that inversion layer, stuck between worlds, it's just going to sit there until that inversion dissipates. There are a few ways that can happen. The sun can come out, start heating the inversion layer, blast through it, churn it all up, and the inversion's gone. Inversions can also move, just like water. Slabs of air moving downhill, or if a light breeze picks up, that whole mass will just go with the wind. When an inversion dissipates with pesticide trapped in it, the pesticide doesn't go away, it just goes where the inversion goes. What an inversion really does to pesticide is gives you zero control over where it goes. It goes wherever the weather takes it. How good is that? Don't you love that? Something we've never seen before, and what's it doing to our pesticide? When does this nastiness happen? That's a 24-hour clock, not a 12-hour clock. Midnight's at the top, and then we go around the scale, there's noon at the bottom, and the end of the day. This is a generalization. Let's say that the sun rises around 5 a.m., and let's say that it drops at 9 p.m., just a day. Let's start at sunrise. Sun comes up, starts to heat the ground, whatever inversion was in place begins to fade, and we're just going to guesstimate 3 hours. That's a good general rule of thumb. No inversion, no inversion, the sun starts to go down, your inversion starts to build. Everything on the ground starts to spit off that radiation. It's at its strongest, nothing's moving at night, and then it happens all over again. So good news, a thermal or radiant inversion happens every single day. So when your label says don't spray during an inversion,
Don't spray at all.
that's a lack of an understanding of what a radiant or thermal inversion is. Give me a break. What we want to talk about
So
is...
it's worst when it's at night, when it's cold.
We'll get there. What I want to talk about is the intensity. Because obviously, don't spray during an inversion means get a new job and stop eating food. Don't spray during an intense inversion. Now we're getting a little closer. Something that's happening in Hort right now is spotted wing Drosophila. Growers are running around with their heads cut off. They're crazy scared of this little fruit fly. It is a brute. It's got an ovipositor on the back that looks like a fret saw, and it can punch through underripe fruit and anything it wants, and it causes wicked damage. If you're a high bush blueberry grower or a raspberry or strawberry grower, your crop can be gone in days. And we don't have any IPM for this. We have no thresholds. It's, oh my God, my neighbor has it? Get out, start spraying now. That means they're spraying insecticides while there are flowers still out. And why do we not want to do that? Because the little bees don't like it. So the IPM people and the nice people that make insecticides give us great advice. They say, no problem, spray at night. Spray at night. That way the bees are all in bed. So, meaning well,
Your inversion.
the conscientious grower goes out as a inversion is building and sprays, goes home knowing they've done something great for the environment and all their friends, and that is where their pesticide hangs until the next morning when it goes wherever it wants while the bees are out. I have no numbers for this, but I am almost positive that if you spray during a strong inversion, you can cause greater area damage than if you had actually sprayed while they were out there. It's that kind of nasty.
But according to your 24-hour clock there, when it's ideal to spray as to wind conditions, it is not ideal to spray as inversion conditions.
Yeah, so you're getting the good message behind this. Spraying during inversion fading is the best choice. when we're considering strong inversions. Spraying during the wind is also not a good choice. Ouch. Ouch. So how do we define what an intense inversion is? Because while there is an inversion every day, intense inversions aren't that frequent. They do happen, but they're not that frequent. Here are a few elements that reduce the intensity of an inversion. If it's a relatively humid day, you're probably in good shape. If there's cloud cover, what happens there is all that long wave radiation that the Earth is spitting off hits the clouds and refracts, comes right back down. Almost like how you can pick up radio stations on certain days that you can't get on others. The radio waves will refract, they'll bend during cloud cover. They'll also bend in inversions, but we're not going to go there because that's even beyond me. Wind. While not always true, most of the time, if there's some wind in the evening, if it's kind of windy that evening, an inversion won't form. It'll help stir that boundary layer up. It won't let it form. So windy evenings, cloud cover overnight, relatively high humidity, you should be in good shape. This is where things get a little interesting, if you're not baffled already. You have to look at where you are. Localized conditions can have significant effects on inversions. That is to say, your neighbor may not be experiencing one and you might. It's that localized. Part of the reason is what the ground is like around you. Think of a radiator. A radiator has a lot of surface area. Those little fins inside, that's so it can give off a lot more heat, more surface area. Or your fridge, same idea. Giving off a lot of heat because of a lot of surface area. If you don't have a lot of surface area, whatever heat's trapped in there only has one surface to come off of. And it's got to kind of wait in line to get access to that surface. But the more churned up or interesting the soil is, or even plants, the faster it can get rid of that heat. And the faster it can spit off that heat, the more likely you're going to have an inversion.